All right, welcome to part three of atoms. How do we know what we know? Last time we talked about John Dalton and his atomic theory. We should have read about Lavoisier and Mendeleev in our readings from the Big History Project, and we had some of the first evidence about atoms and their existence. Today we're going to continue with some more evidence for atoms and essentially proving that they exist. We are going to also learn a little bit more about how Dalton's model of the atom could be improved upon by finding some new subatomic particles. So we're primarily going to be talking about learning intentions 2 and 3 today. And the first thing I want to talk about is something called Brownian motion. This is a chart of Brownian motion. And what this is showing are 3 different particles that are moving randomly about. It's something that you might observe if you have a glass of water and say you get a piece of pepper in it, okay? So you got your glass of water, you got dinner or whatever, get a little flake of pepper in there, and if you watch that pepper on the top of your glass of water, okay, I have some water right here, it might just be kind of cruising around, zipping around on the top of your water, moving randomly about. What this is a map of 3 different particles that somebody tracked and they were moving, zigzagging about randomly. We call this Brownian motion. There's a guy in the 1800s who observed it under a microscope. He had some, I think he was studying what's like pollen or something, and he got some of it in water and it was cruising around randomly, and he's like, that is bizarre, I don't know what it is. I'm going to name it after myself, Brownian motion, but he didn't know what it was. The question is, how does this prove that atoms exist? Well, it turns out that Einstein played a pretty big role in that. We're going to watch this little video here that talks about Einstein's role in Brownian motion and how it provided evidence for atoms.
One thing that's astounding about Einstein's publications in 1905 is that they spanned such a large range of physics. After illuminating the quantum nature of light by explaining the photoelectric effect in March, April saw Einstein turn to something apparently more mundane: particles suspended in fluids. In particular, if you look at tiny particles in water, or dust motes in the air, you'll see that they jitter about in a very odd and random way. That is, it appears odd and random unless you believe that the air or water itself is made up of even smaller particles called atoms or molecules, which just bounce off of each other according to very simple rules. This is called Brownian motion, despite the fact that botanist Brown wasn't the first to discover it, and similarly Einstein wasn't the first to describe it mathematically. But he did draw the conclusion that the mathematical description of Brownian motion is evidence for the existence of atoms, even if you can't see them directly. And then he cleverly derived how big atoms should be based on how much the Brownian particles move. That's like measuring the size of a penguin just by looking at how icebergs jiggle. Talk about cold and calculating.
Okay, so that briefly describes to us how Einstein was able to come up with some mathematical equations that proved that atoms existed. And so what he said is that when you're looking at your glass of water with your little pepper flake floating on top of the glass of water and it's zooming around randomly, it turns out it's moving randomly because water is made out of atoms. And those atoms make up a water molecule, and they're kind of zooming around randomly too. And every now and then, some of them will run into your pepper flake. They'll strike them, and that'll cause it to move one direction or the other. And depending on how that particle of pepper is getting hit in the water, that will cause it to move that direction or the other. And so this was evidence that water was indeed made out of atoms, and it could affect particles, bit larger particles. And he released his paper in 1905 on Brownian motion, and it essentially provided some very good evidence that atoms existed. And it was purely based on mathematical formulas. The next person I want to talk to you about is a guy named J.J. Thomson. And he was able to do some really cool experiments using something called a cathode ray tube, which we're going to look at. And he found the first subatomic particle, so the first particle smaller than an atom. He was able to find it. And he did this around the same time that Einstein was saying that atoms exist. So you can think about if you're just somebody out in the community, not a scientist. On one hand, you have somebody saying that we're made of these tiny, tiny particles, And then right around the same time, we're saying, and those things are made out of things even smaller. It was kind of mind blowing for a lot of people in that time, which is why I think he is attributed to this quote here, which says, "It is the charm of physics that there are no hard and fast boundaries, that each discovery is not a terminus, but an avenue leading to a country as yet unexplored, and that, however long the science may exist, there will still be an abundance of unsolved problems." So what he's saying there is essentially that with every new finding, we're essentially just opening up a door to new questions. And Thompson was definitely one of these people that opened up a door to a lot of new questions. And we're going to look at the first experiments that he did, these cathode ray tube experiments. Luckily, I was able to find somebody who put this video online. I wish I had one of these that we could look at in class, but we don't. And we're just gonna watch this video here and show how this experiment worked.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes, one's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thompson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. We apply one pole of the magnet to this beam and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does it appear as though it's happening to it?
It's moving.
It's moving, it's being repelled, isn't it, by the magnet. When we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thompson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now at the time that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thompson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound?
It's hydrogen.
Because hydrogen's the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle. And it's called the electron. That'll work good.
All right, so that is the cathode ray tube experiment that Thompson did. And essentially what he found was that, hold on, I got to take care of the cat here. Okay, so what J.J. Thompson found was the electron. And it turned out that if we look at his little cathode ray tube right here, there's this beam of particles going through it in the blue line. And when he applied a magnetic force to it, it would get bent. And it bent away from the negative charge and towards the positive charge. And what that meant was that it must be some beam of particles that had a negative charge. And when he did some different measurements around their mass, turned out that they were up to 2,000 times smaller than a hydrogen atom. And it was kind of mind-blowing to him. Like I said earlier, Einstein had just given some mathematical evidence that atoms even existed, and here was Thomson roughly the same time saying, not only do atoms exist, but there's something 1,000 times smaller than them that also exists. It was revolutionary at the time. It was the first subatomic particle that was ever found, and he was awarded for a Nobel Prize for his finding. So this was a pretty big deal. One interesting thing to note is that the electron, it turns out, takes up the majority of space of any atom. And we're going to talk about this later too, but it turns out that essentially if you remove the space occupied by electrons and you stacked up all of our atoms, just basically what's left other than the electrons, our bodies would be the size of a grain of sand. Think about that for a little bit. So basically what Thomson ended up coming up with was a model of the atom that looked like this, whereas Dalton said atoms were these sort of homogeneous things that were just, they're as basic as could be. There weren't any subatomic particles or anything. And here Thomson had found a subatomic particle, so he had to add to that model. And he came up with this model that got dubbed the Plum pudding model. Plum pudding right here we have on the left, where he would say that the pudding part of it is this pink part, is the atom, and it has a slight positive charge throughout the whole thing. And then the plums in the plum pudding are the electrons, and they have a negative charge. So this was a new model that Thomson was able to develop based on real findings, real things that he saw through his experimental evidence with the cathode ray tube. So we are going to pause right now. How do we know what we know? We are going to be thinking today about how scientific knowledge is based on empirical evidence. How was Thomson able to use his skills as an experimenter to gather new evidence? And then compare that to Einstein, who didn't do any experiments, but he still gave the evidence of atoms. What form of evidence did he offer, and how is it different? So for your third paragraph today of your essay, you're going to be writing about the plum pudding model. How is it hypothesized? What evidence is there for it? And also, how did Einstein contribute to atomic theory? How did he prove that atoms existed? Your continued learning today is going to be readings from the OpenStax chemistry book, chapter 2.2. And if you want to, you can also go and listen to J.J. Thomson talk about his discovery of the electron. I like that one because you can hear in his voice that even he was shocked to find that there is something so small at the subatomic level. That is it for part 3. We will pick up with part 4 tomorrow, and you guys can get to work. Thanks.